Thank you very much, Mirna, for that kind introduction, too kind introduction. Okay, so our title is a little bit heavy, Historicizing Extended Constructibility. So extended constructibility is now a technique in set theory or an approach to creating a class of models. So I'm going to tell you about the very deep background that led to this idea. Of course, there were other paths leading to the same thing, but in terms of this particular episode. So I'm going to take us into a very deep tour, as much as I can lay out for you in half hour, of the history of computability in the 30s, as a background again to Gödel's 1946 Princeton Bicentennial Lecture. So this was a session organized at the 200th anniversary of Princeton University. It was founded in 1746. And Tarski had organized a session on computability and invited Gödel to give a 10-minute talk about computability. And that was it. No plenary talk, no 1 hour exposition of the incompleteness theorems or his work in set theory, which by that time he had proven a tremendous result on the consistency of the continuum hypothesis. So he had 10 minutes. So this lecture was later published. It's 2.5 pages, and I think it's one of the most interesting and fruitful of all his work. Just these 2.5 pages. So here's the first sentence of it. He starts out saying, Tarski has sketched in his lecture the great importance of the concept of recursiveness or Turing computability. It seems to me that this importance is largely due to the fact that with this concept, one has succeeded in giving an absolute definition of an interesting epistemological notion, that is to say, absolute in the sense of one not depending on the formalism chosen. He goes on to suggest that, praising Turing very much for what Turing achieved in the domain of computability, and he goes on to suggest that we do for definability and provability what Turing did for computability, that is to say, find absolute notions of these. He calls definability and provability and computability, refers to them as epistemological notions, interestingly enough. Okay, so for the non-logicians or non-set theorists, what do I mean by definability? Well, if you have a formal system, it will be written in a signature, and then you can consider the class of sets or set of sets that are definable relative to that signature. For example, in arithmetic, the prime numbers are definable by a formula in the signature. Oh, I forgot the formal then or and so forth, but and times. But this is a statement in the language of the theory, of the formal theory. So that's what definability is. This is simply what we can say from the perspective of the theory. So situating ourselves inside the theory, what is it that we can say? Okay, so in the second half of this lecture, extended constructibility, Jouko will talk to you about that. This is a means to implement Gödel, this exact suggestion of Gödel. So do what Turing did for computability for, in this case, definability. So we're going to leave provability off to the side and just talk about definability. Now, I want to unpack Gödel's remark about Turing. The import of it, of the Turing machine on his work, was tremendous. So I want to, Gödel is known as a very careful person intellectually, very cautious, but there's one exception to that, and that's the reception of the Turing model. It kind of swept off the table all the problems of the 1930s that had been plaguing Gödel as you'll see. Okay, so the history of computability in the 30s. Gödel employs the class of recursive functions in his landmark paper. Recursion was already known. In fact, primitive recursion was already known, and they knew they could diagonalize out of the primitive recursive functions. So the question was to isolate a mathematical model of the intuitive conception, human effectively calculable. So what is the 1931 paper? Here's the title. We often ignore titles of papers, but the title can really hold kind of a smoking gun, and I think here it really holds a smoking gun. So it's called On Formally Undecidable Propositions of Principia Mathematica. This was Russell's, the formal system that for formalizing mathematics offered by Russell, that Vienna, Göttingen, the logicians were all reading, and they were all proving theorems about that system, more or less. So Gödel works in a fragment of that system. He says Principia Mathematica, so he has a theorem about a specific system, and what he says is related systems. So related systems is very important there. And here's what it says. If you take the fragment of Principia, essentially containing arithmetic, enough arithmetic to code finite sequences and so forth, then if P is omega consistent, that's a small technicality that was later eliminated, then there's a sentence which is neither provable nor refutable from P. And secondly, if P is consistent, then con P is not provable from within. So no internal consistency proof. So a question left open in the 31 paper is the question of the generality of those theorems. So whether they apply to any formal system containing arithmetic, or are they just is there something particular about Principia that makes those theorems apply to those systems? But the general concept of formal system is going to be another matter. So in particular, there's a question whether the incompleteness theorems refute the Hilbert program. The incompleteness theorems were intended as a refutation of the Hilbert program. And a careful reader of that paper will notice that Gödel was very careful to say at the end of his 31 paper that he hadn't shown this. He hadn't actually shown this. And why is that? Well, the assumption at the time was that any formal system acceptable to the Hilbert school must be effective. That is to say, axioms and rules of inference must be, as we would call it today, computable. So the proof predicate, or another way of saying that, has to be something like primitive recursive. So this requires a sharp notion of formal system, and this in turn requires a sharp or adequate notion of, now I'm using the word computability, but actually the adequacy question is, right, to say that you have an adequate representation is to say that it models faithfully the intuitive notion, human effectively computable. So that was the phrase they used in the 30s to refer to the informal computability. Okay, so that's the adequacy problem for, right, it's all over the place in mathematics, right? Continuity is the epsilon delta definition of computability and adequate, of continuity, an adequate notion, and so forth. Okay, the Hilbert program, for just to refresh your memory, if you haven't seen it, very much simplified, and apologies to the people who spent their lives studying the Hilbert program. I'm a little nervous, but this is how I explain it. So the idea is that mathematics consists of an infinitary part and a finitary part, and the idea of the Hilbert program was to show that anything that can be done in the full system, I plus R, can be done in R. So you can get rid of reference to infinitary concepts. And then there was a second demand for an internal consistency proof. So Gödel's incompleteness theorems will refute this. Any finitary system will be incomplete, right? Now, provided we grant the generality of those theorems, and you cannot expect an internal consistency proof. Okay, so I should say, I'm in the statement here at the bottom, I'm betraying, what happened later. So at this point, the theorem's about Principia Mathematica, and Gödel hopes a wider class of systems. But this has not been shown. Nowadays, anyone who asks a logician what are the incompleteness in, they say any formal system. Right? So they grant those theorems full generality. We're really asking what is a finitary proof? What is a finitist concept? And it's very Gödel's letter to Heilbronn, 1931. He says that in principle, it's possible that there are some finitary proofs that are not formalizable in the system that I gave. There's very little prospect. It would have to be a very complicated kind of thing, but I simply can't make the claim that we have a sharp notion of finitary proof at this point. Okay, so in parallel, so this idea of solving the adequacy question for computability, Church introduces the lambda calculus in 1932, together with Kleene. Later on, it kind of loses its logical formulation. Later on, it's formulated in terms of function and iteration. The original presentation of the lambda calculus was found by Church's students, Kleene and Wasser, to be inconsistent. And they even I put the title there, they even put it in the title. So the inconsistency of certain formal logics. Well, obviously they're advisors. So Davis made a funny remark, not exactly what one dreams of having one's graduate students accomplish for one. That's so funny. All right. So the inconsistency, so this is Kleene, all of the people in the 1930s that were writing about this, they wrote beautiful papers in the 50s and 60s and 70s and later going through the history. So what begins to emerge is something that starts to look like the notion of absoluteness that Gödel's looking for. So they have a notion of lambda definability abstracted away from any formal system. Church's thesis emerges. So Church in 33, 34 identifies the lambda definable functions with the human intuitively computable functions. So the correctly formulated. In 1935, Church switches to Gödel's own system of 1934, the Heilbronn-Gödel equational calculus. So Church's thesis will say any computable function will be, any conception of computability will give you the same class of functions as Heilbronn-Gödel or lambda definable. Or by 1935, there were many systems started to emerge. Also, a very beautiful one due to Post in the 20s. They all were extensionally equivalent. They give you the same. You sit down, you think about computability, you write down, you axiomatize the notion or write down some functions and then close under some operations. You are not going to get anything different from what it's quite a remarkable fact that any function that appeared to be effectively computable, that is to say intuitively, was lambda definable or Heilbronn-Gödel definable and so on, was any function that appeared to be intuitively computable was captured by one of these systems. And this was, I'm going very quickly through the history, but this was a lot of work. You had to prove things like the Kleene normal form theorem. You needed a universal Kleene T predicate, and so there was a lot of work done there. So Church's formulation of Church's thesis in 35. Let's say anything that's human effectively computable is Heilbronn-Gödel computable and vice versa. Gödel says this is thoroughly unsatisfactory. So this is a letter to Kleene. And what is unsatisfactory? The proposal that the intuitive notion is captured by the computational models discovered to date, in particular captured by his very own. And he writes later, I was at the time of these lectures not at all convinced. So the question was, the Heilbronn-Gödel equational calculus, it has a very capacious or very generous recursion scheme. But the question is, have you picked up all possible recursions? Okay, so they had confluence. This is the term for that they used, or that Gandhi uses for extensional equivalence. They knew that all the systems were equivalent extensionally, but they lacked what I called a grounding example, an adequate model, right? So they hadn't solved the adequacy question. They had just a bunch of different systems that define the same. Okay, so Turing analyzes effectivity in terms of a fully sharpened mathematical notion, the concept of a Turing machine. It's quite a beautiful thing. If you haven't seen it, pick up a book of Cutland or some and play. It's like a children's game, working out, addition and so forth. It's important to note. Post also. Post was was a city college in New York. So all these people are, England, Princeton, New York City. Princeton and New York City are close to each other, but they might as well be on different planets. So Post in New York has nothing to do with Princeton. But he has a very beautiful model of computation. We call them now Post systems. It's just an absolute delight. So I recommend it. So we have a conceptual analysis of the intuitive notion together with a mathematical analysis. So you have simple instructions: erase, print, move left, move right, and so forth. Turing also solves the decision problem, which was considered to be the most important problem in logic. You have a recursive set of axioms, as we would say nowadays. Is the question whether or not something is a theorem, something follows from that axiom. That's called the Entscheidungsproblem, and it's unsolvable. Now Turing solves it with his method. Church had solved it just before, but by a completely different method. So Turing's, here's Kleene. Turing's computability is intrinsically persuasive. None of the others are. Gödel put things much more strongly. He says the resulting definition of the concept of mechanical procedure by the sharp concept of performable by a Turing machine is both correct and unique. Moreover, it is absolutely impossible that anybody who understands the question and knows Turing's definition should decide for a different concept. So in other words, what is the question? What is the problem? Find an adequate representation of the intuitive notion. He says the sharp concept has always been there, but we just didn't see it. Turing brought us to the right procedure. And here he says you start seeing the word mechanical all over the place. So the machine metaphor comes pouring into logic at this point. I think it's very interesting to track metaphors in mathematics, right? And here the machine metaphor is kind of roaring. Turing's analysis solves the generality issue. It just goes away. He says in a postscriptum to his 34 lectures, in particular of the fact, due to Turing's work, a precise and unquestionably adequate definition of the general concept of formal system can now be given, and therefore the existence of undecidable propositions and also the second theorem can now be proved rigorously for every consistent formal system containing a certain amount of finitary number theory. So, this was the only time, I should say, as a Gödel scholar, that you ever see Gödel just rushing into something. And the interesting thing was, I'll just keep. Turing's work gives an analysis of the concept of mechanical procedure, alias algorithm, or computation, or finite computational procedure. This is just simply equivalent to the notion of a Turing machine. Formal system can simply be defined to be any mechanical procedure for producing formulas called provable formulas. So it's very interesting about Gödel, and I just am writing a paper with a co-author about the Entscheidungsproblem. So Gödel is in Princeton in 1934, and he's giving these lectures about his incompleteness theorems, and he's using the Herbrand-Gödel equational calculus as his system. He leaves Princeton prematurely. There was a crisis, But basically, he goes back to Europe and he says, "Jetzt Mengenlehre." Now I'm going to do set theory. I'm going to forget computability. So the trail kind of Gödel's thinking kind of goes cold between 34 and 36. Meanwhile, in Church and Kleene and Rosser are proving more and more theorems, like the recursion theorem, the SMN theorem, all these wonderful theorems, which are kind of supporting the idea of robustness. But Gödel was doing set theory in Vienna. He was out of it. So there's really if you're trying to track, if you're trying to find the trail of breadcrumbs from 34 to 36 and this absolutely explosive reaction, it's just there's nothing there. So let's just say for the logicians at the time, the Turing machine was not just another one of acceptable model, it was really the grounding of all of them. Gandhi wrote a beautiful paper in 1986 called The Confluence of Ideas in 1936. He says that Turing's isolation from Princeton was the key to his discovery. He makes this beautiful statement. Turing succeeded because he was not familiar with the work of others, the bare hands do-it-yourself approach, but the way in which he uses concrete objects such as exercise book and printer's ink to illustrate and control the argument is typical of his insight and originality. Let us praise the uncluttered mind. I think that's a beautiful, let's pray. He doesn't mean a simple mind. He means he wasn't distracted. Okay, as I said, if you want to think about why the Turing construction was so explosively, had such an explosive impact, there's also this idea of cultural influence. There's this idea of the machine metaphor. The machine metaphor is very old, right? Descartes, of course. There's this reciprocal, the body is to be regarded as a machine can be regarded as a body. I mean, this is a very old metaphor, the machine metaphor. There's also this issue of the technological optimism, technological sublime. This is a phrase of Leo Marx to talk about the conflict between this kind of optimistic talk about industrialization versus this kind of worship of the virginal landscape of, for example, America or some. So the sublime is a site of conflict in a way. That's another story. But I think, this is in the back. This is certainly in the background. So that's the end of the history. Now let's go back to Gödel's 46 lecture. So I started out reminding you of the first sentence. He says, he praises Turing computability. He says that the definition Turing gave was an absolute notion. That is to say, formalism independent. So that's textually there. Completely analyzed, final, also absolute in the technical set theoretical sense. Gödel is using the word absolute in different ways at different times. So he continues by saying, as far as provability and definability are concerned, it's clear we haven't found these absolute notions, right? Being definable in set theory is paradoxical. Take the least definable or undefinable ordinal, you've just defined it. And of course, for what he called demonstrability or provability, you have the incompleteness theorems. So we haven't got absolute notions of. But he says, nevertheless, we shouldn't be discouraged. I think we should expect the same thing to do what Turing did, to be possible in the cases of demonstrability and definability. He says, we have been hindered in terms of making a definition of the absolute notions concerned, but it's not, we haven't ruled out the idea that we may be able to define these concepts in an absolute sense. So as far as provability, he suggests large cardinals. This leads to Gödel's program in set theory, a program of large cardinals. This is 46. the famous, it was 1 year later, what is Cantor's Continuum Hypothesis? He lays out Gödel's program for large cardinals. And then, so here is what he proposes for definability. Now, constructibility, he's already invented the constructible sets in 1934, actually. He publishes it in 1937, the constructible sets. So this is an iterative hierarchy. It's not the full hierarchy. So you start at 0, and then you pass from one level to the next by collecting up all the sets definable, in the sense that I spoke about at the beginning of this lecture, by a formula in the language of set theory with parameters from the lower level. So those are the new sets you add. You don't add the full power set, for example, of a set. You just add the definable power set. So that's one. So he toys with the idea that constructibility might be the absolute notion that we're looking for. Notice constructibility, we're building the constructible universe using the ordinals as a spine, using these canonical well orderings as a spine. And then he proposes hereditary ordinal definability. So we say a set is ordinal definable if it's definable with ordinal parameters. It's hereditarily ordinal definable if it's ordinal definable, and the set is ordinal definable. Every member of the set is ordinal, every member of member, and so on. So every element of the transitive closure is ordinal definable. And Gödel says that there's nothing more law-like than the tower of ordinals that on which you build the constructible hierarchy, or which define the ranks of the cumulative hierarchy. Right. So some people, there's a little mini spat among historians of set theory. What L stands for? Why Gödel put so? I think it was some people very close to Gödel suggested L for law-like, but there are other proposals. But anyway, this is so canonicity, right? We're looking for absoluteness, or at least some form of the notion being canonical, so law-likeness. Okay, so these are Gödel's two notions of definability. We have two canonical inner models, the constructible sets. These are a model of GCH. This was the famous result of 34. And then we have the hereditarily ordinal definable sets, also a model of ZFC, but the CH can go either way. So this talk is about implementing Gödel's suggestions. So what would it mean to transfer what Turing did for computability to the problem of definability in set theory and finding an absolute notion of definability in set theory? So what is the template? You look for confluence, and then you look for an absolutely adequate grounding example. So the idea here is, you notice that the constructible sets are built over first order logic. So how do you look for robustness? You take the constructible sets, and then you replace the first order logic over which they are built with other logics. And then you see. So that is the implementation suggested here, and that's what Jouko is going to talk to you about. Okay. Yeah. Jouko's going to use the board.
You can put in a pocket.
I will
I put in
not need it here. Yeah.
1, 2, 3. Okay.
Yeah, good. You need
No.
computer? Okay, so I will.
Just
What's
that?
We have 2 hours.
Yes, yeah.
You
Yeah.
have 5.
Right, I know, but Jouko will feel he has to finish.
No, you don't have to feel anything. You can finish anytime. projectors. Voilà, c'est fini.
And can you give me the eraser?
Oh.
Okay, thank you very much for this opportunity to speak here. Thank you for the invitation. And I continue from where Juliette left. So let me first remind you of the problem that really has characterized set theory research for 400 years and was motivating question for Gödel, Continuum Hypothesis. So if here are the real numbers and here are the natural numbers, then if you take any set of real numbers, then the hypothesis says that either there's a one-to-one mapping here or there's a one-to-one mapping here from all reals into this set, either or. Now, of course, this is an extremely bold. Anyone would say it would be a miracle if that was the case. Why would it be either one-to-one from here or one-to-one from there? There's no reason. So it's sort of obviously false, but it's extremely difficult, as it has turned out, to pinpoint a counterexample. So one could say that it is still motivates. It's an intriguing question, and what is really the heart of the matter here is that this set here is an arbitrary set of reals. What does that mean? What does an arbitrary set of reals mean? That is the heart of the matter, because I didn't say a Borel set, I didn't say a closed set, I didn't say a definable set, an arbitrary set. What does it mean how do you take an arbitrary set of reals? This is really the problem, and this is what Gödel in the 30s was puzzled by. So what Gödel showed was that CH is consistent. So this is very important because it means that you cannot we cannot solve it, but at least we cannot derive a contradiction. So it's sort of safe to assume it. That was a very important aspect, because otherwise some smart person derives a contradiction from it. Now it's important. So how did Gödel do this? This is very early in logic, and he introduced things which became important, such as an inner model. And it is called L. In fact, for Neumann already in his doctoral thesis, he introduced the concept of inner model and the possibility that it is used for independence results. But it was just a theoretical speculation at that time. But Gödel actually gave this inner model. I think the picture was already there. So there is this transfinite hierarchy. We go over ordinals. We start from empty, and then we keep adding all definable first order definable subsets of the previous level. So you start from empty set, and then when you have reached some level, then you look at all first order definable subsets from here, and you put them onto the next level, and then you look at subsets on this level, and you put them on the next level, and you continue like this, and then you take unions when you have a limit, and in this way you get this so-called inner model L. First order logic here means formulas which have epsilon, identity, extensor quantifier, universal quantifier, conjunction, disjunction, negation, and so forth. Yes. Okay. So the so-called language, first order language of set theory, which was very not well known at that time, advocated by Hilbert, for example. Okay, so what Gödel does is in the whole universe of sets, which we call V, he defined a sub universe. So he went from X is a set to X is a set and X is constructible. So constructible means element of this hierarchy. Okay, so this is an interpretation. He interpreted being a set by this more restricted set. Not only it's a set, but it's even a constructible set. Not because every set is constructible. No, it is just interpretation. It is it's a deliberate, opportunistic interpretation. Whatever crazy thing this is, and it's a bit crazy. In fact, when you study it, you just put it as a condition there, and then the CFC axioms, the Zermelo-Frenkel axioms, are true in L. So this reinterpretation of the set still satisfies all the axioms. And in addition, CH is true in L. So whatever one thinks of this universe, and Gödel immediately understood that it is not proper thing to think that it is everything. It is useful in showing that in that strange universe, CH is true. So and all the axioms are true. So it means that you cannot derive a contradiction from it. Okay. As I said already, Gödel said that you shouldn't think that all sets are constructible, because it's an arbitrary restriction. In mathematics, we do whatever we like. We don't want to be constrained to doing only things which are constructible. By the way, this word constructible should not be confused with constructive mathematics. There is nothing constructive here. It is just that this he just introduced that word. Well, here is a kind of a constructive, but it is not what is called constructive mathematics. Okay. Now, as Juliette said, we try to find canonical inner model. So this is an inner model. This here. And something which is robust, and it has such simplicity of definition as a Turing machine, so that it would, like Turing machine in definition of computability, became like the immediately like the generally accepted. So can we find such concept? And L is not such a concept because L does not have so-called large cardinals. Okay, now the large cardinals are things which are inaccessible. So an inaccessible cardinal is kappa is inaccessible if lambda less than kappa implies 2 to lambda is less than kappa, and also kappa is so-called regular, so it means that kappa is not the union of smaller sets. Okay, but there's a stronger concept, measurable cardinal. If there's a kappa complete, non-trivial, non-principal ultrafilter on kappa in the power set of kappa. And Dana Scott in the early 60s proved that there are no measurable cardinals in L. So okay, so let me first say a few words. Why should we care whether there are measurable cardinals in L or not? Measurable cardinals and the bigger one, cardinals called Woodin cardinals and supercompact cardinals have become known in over the last 100 years or over the last 20, 40, 30 years that they are very useful. In trying to solve these kind of problems, like what kind of definable counterexamples to continuum hypothesis can we have? Can we have projective, analytic, co-analytic? Already 100 years ago, it was known that you can't have a Borel, but okay, it started with Tony Martin from Los Angeles. He proved that from a measurable cardinal that such a counterexample cannot be a projection of co-analytic set. But then more large cardinals were used later by Steele and Woodin and Martin to show that there cannot be a projective counterexample. A projective set is a set which is obtained from Borel sets by iterating, taking projections, continuous images and complements. Okay, let me say briefly how Scott proved this, that there are no measurable cardinals. So he constructed an ultra product. So in general, ultra product, you have here is a measurable cardinal and here is some model. In Scott's case, it is actually V, but let's think a simpler case. It is just some set or model. Then you take all functions from kappa to m, and then you identify if they are equal, unlike here. Well, here they are. But if you can find a set in the ultrafilter where they are equal. So if they are on most arguments equal, then you identify them and you get a reduced product. And if the filter is ultra filter, then that's an ultra product. So Scott found a way how to do this for the whole universe V, and he got an inner model, a new inner model, into which V can be embedded, so that kappa is moved, but everything below kappa is fixed. And what is interesting about this is that we had here this ultrafilter U, and it's actually easy to see that U cannot belong to this inner model, because this is an elementary mapping. It preserves all first-order definable properties. Kappa, if we assume that kappa is the smallest measurable cardinal, then I kappa is the smallest measurable cardinal here. So this kappa, which is element of M, is not a measurable cardinal. So this ultrafilter cannot be there. So, but because this is if this here, suppose this satisfied V equals L, this already Gödel realized that you can write this in a first-order formula, with a first-order formula, and therefore also here this would be L. But it cannot be the same model, because this ultrafilter is missing from there. So this has become a very important idea in modern set theory, because you can then iterate this, and you can iterate it even over all ordinals, and you get what is called core model, which again is not L. Okay. So now the situation is that if you are looking for a canonical model, L is very good. It's forcing absolute everything, but it doesn't have so-called large cardinals. It has only sort of small large cardinals. So we need something more. What happened then was people like Solovey and Silver and Jensen, they defined a version of L where you throw U in, and then you have a model which has a large cardinal. But there is something wrong with this model. Well, sort of. Wrong is wrong word. Wrong is not the right word. But what I mean is the following. This ultrafilter exists because of axiom of choice. Without axiom of choice, you cannot construct in an infinite set a non-principal ultrafilter. In fact, they are sort of almost equivalent, axiom of choice and the prime ideal theorem. So such ultrafilter is bound to be somewhat arbitrary. It's like things you construct with axiom of choice, non-measurable set, paradoxical decomposition of the sphere, and so forth, is a kind of random object. So is this canonical? Well, Kuhnen in Wisconsin proved things about uniqueness of it, and so it is. There is some canonicity, but anyway, it is a little bit ad hoc, because you take an ultrafilter, then you construct a model, and of course there are no. You have one measurable cardinal. You don't have two measurable cardinals, so then you need two measures. But then you don't have three measurable cardinals. Okay, so then you have you continue like this, and you continue over all large cardinals that you like, and this leads to a so-called inner model program, and which the ultimate L of Woodin is kind of the ultimate object there. Okay, but one can argue whether these are canonical or not. I don't want to say anything bad about this, because this program is extremely successful program in set theory. But we take another approach in my work with with Juliette, and so it's and Makidor and myself, still unpublished work, where we try to find something more.
The first paper is out in the JM.
Yes, but what I'm talking about today is in the second paper, which is not yet. So part one is published, part two isn't. Okay. Anyway, it's kind of very fresh. And we go into this Gödel's definition, and we focus our attention on this. Why first-order logic? There are many other logics. There are generalized quantifiers, there are infinitary languages, higher-order logics, and so forth. What if we vary this here? What kind of version of L we get? Certainly, if we put here an extension of first-order logic, we get an extension of L. So extension all the same, right? Yep. So suppose we take L star, which is extension of first-order logic. I will mention a few extensions.
You shouldn't call it L again, because now it looks like a constructible universe.
Wait. Who's the boss here?
Me, I'm the chair.
Sorry. Oops. Okay. So if we modify the Gödel's definition by putting there an arbitrary logic L star, what we get is an inner model which we denote by CL star. So CL star is just like L, but instead of first-order logic we have into here we put a logic L star. Yeah, there's a confusion about else there, but cannot. What's that?
Script L for the
Who's the boss?
Well, the democracy is the boss, but now everybody's telling you to change.
Yes. I have gone through this many times, and still I stick to this. So CL star is now Gödel's L with first order replaced by this new logic L star, and of course now it's interesting what kind of L stars we can have. So in first order logic we have usual extensor quantifier for x phi x, which means there is an A such that phi A. So when we define over a proportion, we can ask, is there an is there an A here? Okay. But Andrzej Mostowski introduced the generalized quantifier Q0. There are A0, A1, etc., or different, such that phi AI for all I. Okay, so that means that it says that there are infinitely many X. It's well-known elementary logic exercise that this is not first order, so this is so-called LQ0. Then there is Q1 for all A0, A1, etc. There is A which is different from all of these. Such that phi A. So phi is satisfied by uncountably many. And in both of these cases, L is the same. So first order, which is L, really the L, is the same as this, which is the same as. And a lot of things like extensions of first order like this do not lead out of L. So L has a lot of robustness. It is invariant under the chains of logic to some extent, but meh. Let's look at the following. It is kind of getting hot in my pocket, or is it this? I think it is. Yes. Yes. Is it okay? Okay, it's not going to explode. Like, have you had this in an airplane? Okay. So let's look at the following. We almost all S phi S. It's the following quantifier. We play a game between 1 and 2. 1 plays A0, 2 plays A1, 1 plays A2, 2 plays A3, and so forth. And 2 wins elements from here. If phi holds over the set like this. Now this quantifier, which is just kind of slightly more complicated than this leads to this logic this model CAA, and this is different from L. Well, under of course, if V equals L, then everything is equal to L. But if there are large cardinals, very small large cardinals, for example, a measurable cardinal, if there's a measurable cardinal. Okay, so now one can ask how robust is the AA model. And okay, facts. The game is determined. So this, I have to assume now something. I assume large cardinals without, or proper forcing axiom, whatever that is. one has to assume something, otherwise this doesn't start to fly. The game is determined, which is very maybe surprising, but this is a phenomenon in modern set theory which is very useful. CAA has a proper class of measurable cardinals. And more. In fact, it's you see, because I say now, maybe it's too quickly for part of the audience, but because this is determined, it means that the filter we obtain by taking the definable sets of countable stationary the non-stationary sets or definable sets of countable subsets is an ultrafilter when restricted to this AA model because of the determinacy. So on every regular uncountable cardinal, the non-stationary ideal when restricted to CAA is a measure, normal measure. So all uncountable cardinals of V are measurable in this 3. CAA is forcing absolute. Okay, and I started by asking this question, and I noted that Gödel was motivated by this question and defined L, and he was able to show that CH is true in L, and here also. So we get the same kind of things as L, but we get large cardinals which L doesn't have, and so because of this forcing absoluteness, I claim that this is somewhat robust and canonical. Also, it is not defined the way I define it. I define it by this game. I don't define it like, let's use Axiom of Choice to get a non-principal ultrafilter. No. I don't start from any strange objects. I start from scratch and I define this. And then if the universe happens to be so nice that there are large cardinals,
you should say who the force result.
What?
You say who this CH is due. The CH result is due to steal.
CH is true is...
The theorem is due to Gabe and to John Steele.
No, this is not. GCH.
Oh, sorry.
Jouko, could you just tell the audience how to mean by forcing absoluteness?
Yes. Forcing absoluteness means that what any sentence which is true there is true if and only if it is true in a forcing extension, in any forcing extension. So all forcings preserve truth in this. So this CAA does not depend on forcing. I didn't talk about forcing earlier, but forcing is the method introduced in the 60s by Paul Cohen to make models a little bit fatter, and so fat that they fail continuum hypothesis, for example. But it has become, in addition to inner model construction based on the Scott ultra power, the forcing has become like the second main technique in set theory. But that technique doesn't help here to get independence results. So because of this, this gives credibility to decidability. So for any phi, whether CAA satisfies phi should be like decidable. We should be able to decide this question, because you can't change it by forcing. So it's not a proof, but it seems that it should be. So like we have done here. Okay. So I was going to prove the continuum hypothesis, but I can, if somebody wants, I can give say a few sentences about it. But the point is that we think that this is a canonical, robust inner model, which is always definable, and under some set theoretic assumptions, it behaves in a way which is somehow considered better than L, and it doesn't have the. It's kind of parallel to this. I don't want to say anything bad about the competitor, but the question now is that can we go to stronger and stronger logics like this, and get more and more large cardinals? We have here just a proper class of measurable cardinals. We would like to have, with the stronger logics, we would like to have the Wooden cardinals and even strongly compact or something like that, but that we have not done and don't know how to do. So this is my continuation to Juliette's introduction.